So hi everyone, we're back in our videos in number theory, and in this video I'm going to show an example of the application of the first principle of mathematical induction, also known as the weak version of induction, and we're going to answer this question over here. Okay, so we have a proposition. The proposition states that for every, that is for all small n, which is found in the set of integers, this is always true. So twice that small n that we have here is less than or equal to 2 raised to a certain n. So we're going to prove that by induction to show that that is true for every n in n. And, that's the purpose of induction, right? So we're going to prove it that it's not only true for some certain n, but it's true for all n in the natural numbers. So we're going to prove that and show proof by induction. So let's start it by showing. All right, I'm gonna use that. Change color. Let's make it blue. Okay. So proof. So that it will be like an elementary proof. We're gonna use by PMI, or you can say in some books they use by induction. That's also just the same. So we're gonna first start with an opening statement. We will let our P of n, that's our a statement, and be a statement that means that 2n is less than or equal to 2 raised to n, and this is good for all n in the natural numbers. Okay, so that's our opening statement. We're gonna continue off with our base step. Remember that for those who are not using or we're not familiar with induction, we use induction to prove statements for all natural numbers, or from any starting natural number up until any n in the natural numbers. And we have two steps: the base step or the basis step in some books, and the induction step. So pretty much you can watch my previous videos to see the theorem there. So we're going to start with the basis step. Okay, so I just want to highlight that. So for the basis step, our statement here basically starts with 1 because our n is a natural number, is in the natural numbers. So our smallest value is 1. So we will say take n be equal to 1. So if we have 1, so we have p of 1 is actually equal to the statement 2 times 1 is less than or equal to 2 raised to 1. So notice that if this happens, this is true because 2 times 1 is 2, which is actually less than or equal to 2. So that, the equal sign, if you're going to highlight the equal sign here, that is true. So 2 is less than or equal to 2. Actually, it's equal to 2. So therefore, with that one, the basis step is proven. So therefore, the basis step holds. Okay. So we're good for the basis step. So meaning it works for the first integer or for the first natural number. We're going to go ahead with the induction step. And here, remember that we're going to take an arbitrary integer k, and we will assume that it's true. That's our inductive hypothesis. And if p of k is true, it follows that p of k plus 1 is also true. So we're going to take an arbitrary n to be equal to k. So that's an arbitrary choice of n in the natural numbers. So remember, so if n is equal to k, k should be 1. K should be a natural number because n is a natural number. So I won't state that anymore. Take n equals k. So therefore we have p of k is therefore be equal to the statement 2k, which is less than or equal to 2 raised to k for a certain k in the natural numbers. Okay. With that, we will then say that this is our inductive hypothesis. So we're hypothesizing, or what is that the correct term? We are making an hypothesis that this statement is correct. So in sum, we will try to box that statement so we won't get lost. We should use that statement anywhere, somewhere in our proof in the future. So that's it. By our theorem in the first principle of mathematical induction, um, suppose, or we will assume, that P of K is true. So this is the hypothesis of the second condition. Then we can actually say that P of K plus 1 is also true. Okay. With that, so we have our P of K plus 1 will be equal to the statement 2 times K plus 1 is less than or equal to 2 raised to K plus 1. Okay, sorry. Okay, K plus 1. Cool. All right. What did I do? Anyways, all right. Um, what we want is to prove that this statement is always true using our inductive hypothesis. So we will continue with that is 2 2k. We're going to distribute this thing here. We're going to using distributive property, and then I guess that's pretty much clear. And also we're going to make use some statements in the statement in the laws of exponents that states that let me just put that. So okay, so we have a law in exponent. Just recall, just gonna put it right here. Recall that we have a certain law of exponent, that if we have law of exponent, I forgot the name. Is it the law of power? I forgot. Law of exponents, forgot the actual name, but I know that it works like a n times a m is actually equal to a times n plus m. So basically, with this thing in mind, we are actually adding two numbers. And if we do that, two numbers, I mean two numbers in the exponent of base, we call it base, right? And that happens, this addition happens, if we have, this is equal to from the same base and the exponents are different, as long as the bases are the same. So we're going to apply this here so that we can expound that a bit. So, all right, what will be the next step then? So we have, well, we know that in the left hand side, we're simply just going to distribute. So this becomes 2k plus 2 is less than or equal to 2 raised to k times 2 raised to 1. Okay, I hope that you see where this is coming from. So this is actually coming from the law that I said that we will recall. So that's where this is coming from. So let's fix that, shall we? So this becomes 2k plus 2 is less than or equal to, so 2k times 2 raised to 1 is 2. So we can simply say that twice the 2k. All right. So in this portion, we will actually now need to apply our inductive hypothesis, this one here. So how can we apply that? Using some law, the law of equality. If we're going to add something in the left hand side, we should also add something on the right hand side. So what I'm gonna do is I'm gonna suppose that our P of k is actually equivalent to the form 2k plus 2, which is less than or equal to 2 raised to k plus 2. So I'm gonna use that instead of the original statement. So what do we have here? We know then 2k plus 2, using the inductive hypothesis, 2 is less than or equal to 2 raised to k plus 2, and all of this are all less than or equal to 2 times 2 raised to k, indirectly saying that 2 k plus 2 is less than or equal to 2 times 2 raised to k. So that ends actually, that completes our inductive hypothesis, that it holds that in all, for the statement p of k plus 1, this statement always holds. So therefore we stop at then the basis step, not the basis step, the induction step holds. Now with this, we can say that, we're actually done. Then by the first principle of mathematical induction, the statement, what's our original statement? Here it is. 2n less than or equal to 2 raised to n is true for all n in n. And let's stop that with a QED. All right, perfect. So that's our practice for today. Thank you very much for watching. I hope you learned something now. And okay, I'm gonna try to make more of these, and that ends our video now. So thank you very much for watching, and see you soon. Bye.